In this lecture, we're going to talk about modeling, statistical models, association models in this case, and things like regression, and then a related concept, correlation. The idea is that statistical models try to predict what's going to happen based on association. There are some keywords. The dependent variable is the outcome variable. Independent variables are the explanatory variables, and they're there to try and show relationships and explain or predict outcome variables. Correlation and R squared. A statistical model, dependent variable equals independent variables. We have the simple model, y equals a plus bx, and then you can have a multiple regression where we have y equals a plus bx, b2x2, all the way up to whatever, plus an error term. We'll talk about slope, the amount of change in a dependent variable for each unit change in the independent variable. That's the b's in that equation above there. A regression of coefficient, which is just another name for slope. Intercept, the value of y when all x's are 0. Residual variance, variance that is not accounted, variability that's not accounted for by the model. So what you make a prediction, and when you're off, that's residual. Range restriction. Well, this is a very common problem that you'll see in papers where correlation doesn't seem like it's very high, but one reason is people are using a restricted range, like they use all normal patients when they're looking for a test rather than looking for normal and abnormal. So correlation accounts for the relationship in variability. If there's no variability, there's no correlation. Multiple regression was this little model up here. It's more than one independent variable. Logistic regression is a situation in which the y is not continuous, but it's discrete, like yes or no, sick or not sick, died or not died. Statistical control is the controlling for nuisance variables by incorporating them into the model. For example, you really want to know about the relationship between y and b1 or x1, and these other variables just control for nuisance variance so that it isolates this relationship here, and that's pretty handy. So we're going to start with the Pearson Correlation coefficient, and that is a basic standardized index of association. It measures the linear relationship between variables. It varies between -1 through 0 to +1. 1 indicates a perfect association between two variables. If you know one, you know the other. And the +1 and -1 are equally strong. It's just minus goes in one direction and plus goes in another. Correlation is a frequently used measurement, but it is much more useful when you square it and you get R squared, and we'll talk about that a little bit more. 0 is no correlation or association, it's just random, it's chance. Whenever we talk about statistical tests associated with the correlation R, we're referring to R equals 0. So you could have a significant correlation of 0.2, which isn't a very good correlation, but it's not chance. A weak rule of thumb is that when R is greater than plus or minus 0.30, then it's a minimal point of clinical relevance. This is really pretty arbitrary, though. There's a lot of things going into correlation besides just the clinical relevance part. It depends on your measure that you're using, too. Some measures have a lot of variability inherent in them, measurement error, like paper and pencil tests. And so you would not expect those to be as correlated as something like objective blood tests that you're comparing to each other. Okay, so Our top little graph here is a correlation, what a correlation looks like when there isn't one. R equals 0, this is the x-axis right here, and this is the association of y to the y-axis. And you can see if you know x, you don't really know y, because at -2 they're going kind of all over the place, 0, 1, 2, and while most of the points are in the center, you get kind of this oval. There's really no relationship. Here we have a correlation of 0.8, and you can see if you know what the x value is, you do know a little bit more about what the y-axis could be. Although even when the correlation is 0.86, remember it can go to 1, there's still a lot of variability in there. The same way here, we have a correlation of minus 0.86. The only difference between these two is one is going up. As x goes up, y goes up. Here, as x goes up, y goes down. The strength of the relationship is the same. And when we talk about r squared, squaring that coefficient, that's the amount of variance that is shared between the two. In other words, well, we'll talk about this a little bit later. Here's our clinical relevance rule of thumb. Now, this looks pretty close to 0, but there is a slight upward slope, and that's what we're calling minimal clinical relevance. It's really not much of a correlation. 0.9 isn't too bad. That's pretty good. And you would expect that in objective measurements. Now, here is a correlation of 0.53. And this particular example we got from a study that I did a number of years ago, in which we called up kids that had diabetes type 1 and asked them what their blood sugar was. And if they hadn't tested it, they would go while the computer waited. The computer made these phone calls. And so we wondered if the kids lied or not. So we correlated their blood glucose levels with their glycosylated hemoglobin levels. And glycosylated hemoglobin you take when you go to the doctor, you get this measure, and it goes back about 90 days. So in the previous 90 days, we looked to see what they said their blood glucose was, and then we looked to what the HbA1c was. And we see that there was, I would say, a clinically relevant effect. The correlation was 0.53. In other words, they shared about 25%, 0.53 squared, about 23% of the variability. It wasn't perfect, but then blood glucose and HbA1c aren't perfect even if you do them at the same time. So it showed that the kids were most likely being pretty truthful when they reported their blood sugar levels. A perfect association is R equals 1. Here's a perfect positive. This is Fahrenheit as a function of Celsius. This is the formula. And if you know Celsius, you definitely know the Fahrenheit. So that's a perfect correlation. Here's a scatter plot of a correlation between baseline axial length down here and 5-year axial length. And these kids got this particular Ortho-K design. And the line of identity is right here. So we have an R square of 0.88. That's like a correlation that's pretty high. You're accounting for 89, almost 90% of the variance. But you should note that while you're accounting for this variance, the scales don't have to be necessarily identical. So there is this basically a little bit of a shift upward from the line of identity. In other words, if you were at this crossroads point right here, both baseline and follow-up have 23. So values falling below this line mean that axial length was shorter after 5 years. not really something that's probably possible. This is more of a measurement error likely scenario. All right, so that's basically a discussion of correlation, this association. Now let's get a little bit more heavily into simple linear regression. So the formula is y equals a plus bx. A is the intercept, so when x is 0, y equals a. So the intercept is y. The intercept is the value of y when x is 0. Y is the dependent variable, it's what you're trying to predict. B is the slope. And a slope means that for each unit increase in x, you multiply the slope times that x, and you get the amount that y increases. If there's no relationship, then the slope b is 0. It's a flat line. It doesn't help you. Knowing x doesn't help you predict y. And you can predict y values by just plugging values into this simple formula. Here we have a scatter plot and a regression of 5 years. This is that graph we showed a few minutes ago. And this is the formula, y equals 1.0385x minus 0.5217. So basically, for every unit increase in x, you get just a tad more than a unit increase in y. You can see that the red line down here is a little bit closer to the line of identity than this one. So it has just a tad greater than slope of 1. And when we talk about percent of variance accounted for between the two, or knowing how much is accounted for, all of the variance is, when we talk a total variance, is the y value. So if we squished this whole x, if we put all these values down and made them all the same, or just got rid of it, and looked at the y values, this would be the spread of the y's. And you can see here that this is the spread of y when we don't have x. When we do put x in there, our spread is much smaller. It's this amount. This is the proportion of the variance that's accounted for. Well, actually, 1 minus is the residual. The error is this small amount of variance proportionally related to this. And 1 minus that small amount is the percentage that's accounted for. So when we have a high R squared, the points are close to this red line. When we have a low R squared, the points are farther away, and they come closer to the variability of all the y's. So again, this box plot here represents all the variability of y. And the little piece that's around this line is this little portion of the variance that's not accounted for. So, kind of given an egg and started talking about the meaning of the residual. Residual means error, it's unaccounted for variability. The residual is the actual y minus the predicted value of y. So the red line means the predicted, and the actual value is the little dot, and the actual minus the predicted is the residual. Residual includes measurement error, that is a kind of mistake. Residual also includes other explanations or sources of variation. For example, age might be something that would contribute to the variability from baseline. So if you started out older, as an older child at baseline, you're going to have less residual around the model than if you started out young. And multiple regression is used to account for that additional source of variance. So for example, we have, if we're looking at different kinds of lens types in an Ortho-K or a multifocal contact lens study, we look at baseline values to get rid of that extra variance. We don't really care about at the beginning. We want to know how much does the lens type affect axial length without having to worry about where it started from. And that's a controlling for this nuisance difference between people at baseline. So to kind of continue this a little bit, if we look at this point right here, we can see it's at a value of maybe 24.5 and on the x-axis, and the difference here is the residual. So this length of y is the residual. This red line, same place, 24.5 on the x, is going right to there, and that's the predicted value. So the difference here is the residual. And not to beat a dead horse, but basically I want to again show you here our baseline values: 25.38, 24.97, you know, it's right in there, and so forth. And then the yellow is the actual value. So your baseline was 25.38. If we come up here, we're going to find an actual one of these points. It's going to be 25.64. The actual value. The predicted value when it's 25.38, the point that's on the line at 25.38 is 25.84. And when you take the follow-up and subtract the predicted, you get the residual. So that's what we were showing on this graph. The actual minus the predicted gives you this follow-up, the residual. Now, the follow-up, all these y values basically in our equation, these are the y equals a plus px. This follow-up has a has a total standard deviation of 0.95. Square that, you get about 0.90. The predicted values, they also, if you look at all of them, come up with a standard deviation of 0.89. You square that and you get 0.8. All the residual values, if you add those and calculate the standard deviation, it's 0.32. Squaring that is about 0.1. So the total variance is 90. That's 80 from the model, 10 from the residual, for a total of 90. The proportion of variance is 80 divided by 90 is 0.89. 0.10 divided by 0.9 is 0.11. You add those two up and you have the total amount of variance. So if you know the model variance, and you can, the proportion, the r squared, basically, that's what this is, the r squared, the proportion of the total. And you multiply, or you subtract that from 1, and the proportion that's not there is 11. So, that's where all those numbers come from and why they do. Now here we have, we saw this line before. That was the one type of contact lens. This was another. Now you can just tell that at 24, this aspheric design, they grew about that much. But the other ones, the spherical design, they grew a whole lot more. They're up here. And they both have a pretty straight line. There's a little bit This one, as the kid gets older at baseline, for older children who are older at baseline, tended not to have quite the same amount going up, but their correlation is 0.8. The slope, or not correlation, but the slope is 0.8. So for every increase in x, you get a 0.8 increase in y, whereas here, for every increase in x, you get a 1.0385 millimeter increase in axial length. And again, this is the line of identity. You can see the eyes are all growing a little bit. The aspheric one doesn't grow as much as this one. So baseline, follow-up, each dot is a person. It's a person at baseline and their person at follow-up. And the triangles represent one group that got spherical lenses. The circles represent another group that got aspheric Ortho-K lenses. So that's how you read these, and you know that for this one you can see the circles are pretty close around that line, so that's 89% of the variance. The triangles are spread out a little more, and they only account for 60% of the variance. Now we have this concept of range restriction, very, very common in the literature, and it's a big problem because people just they don't have a lot of variability. So you can see here we have exactly the same points as we do here, only we've cut them off right here. These points are the same as these points up to this point. My scales aren't the same, which is unfortunate, but you can see if you keep going, we've accounted for 59% of the variance. This one we're 40%. So if you're doing a paper and you're just doing normal people where you have Goldman versus another measure of IOP, it looks bad if you just look at normal patients. If you add people that are normal plus people that have hyper intensive ocular pressure, then the correlation is better. The instruments aren't changing. It's just a statistical artifact of chopping it off. So the point here is that if you don't have a lot of variability in your X, you're not going to find as much variability in your Y. And there's kind of a fun example with nursing students that I did many years ago, and maybe sometime in a review session I can talk about that. Okay, cause and effect. Correlation and regression are statistically methods of association. They do not directly demonstrate cause and effect. Even if a correlation of 1, the Celsius of 100 does not cause a Fahrenheit of 32 degrees, or 212 degrees boiling, as a Celsius of 0 doesn't, or a Fahrenheit of 32 doesn't cause a Celsius of 0. They're associated. They're not cause and effect. Even though the x-axis is used to predict y, we cannot say x causes y. However, you can put on your doctor hat and determine if it makes sense that x causes y, and you can treat it that way, but it's not a statistical conclusion. All right, so what have we learned? Correlation shows association between two variables. When p-values are reported, they are used to test the null hypothesis that r is 0. In other words, it tests whether that linear relationship between the two variables is strictly, those points that you get, is strictly chance. Now, they're not going to be exactly 0. they're going to be, but the null hypothesis is that they're 0, and if you reject it, then you conclude that there is something that isn't chance. The R squared is the amount of variance in Y explained or shared. We often say shared rather than explained because it's not a cause and effect. It is the correlation's effect size. And while associations may be greater than chance, it may not be very large. That is, it may not be clinically relevant. And our rule of thumb is a little weak in correlation, but R values greater than 0.3 start to reflect clinical relevance, meaning that they account for about 10% of the variance. Not a lot, but clinically relevant, as is 0.5 clinically relevant in the difference between two means, but it's not a very big difference. So that's it. Thank you.